Hi, I'm going to talk about fault friction in non-isothermal conditions. Laboratory experiments have shown that friction is a thermally activated process whereby a sudden change in temperature induces a direct weakening effect followed by time-dependent healing. This effect is important to understand because of potential positive feedback with shear heating that may induce thermal instabilities or different rupture styles. The velocity dependence of the frictional response is well understood with potential velocity weakening or velocity strengthening properties. However, the velocity dependence is often associated with a typical temperature dependence. For example, velocity weakening friction is often typically associated with temperature strengthening, and velocity strengthening friction is typically associated with temperature weakening. This effect is most pronounced at temperatures above 350 degrees, corresponding to the mid-crust or lower crust, where the temperature weakening is significant and sometimes exceeds the variations of friction induced by changes of velocity. Beyond temperature effects, the frictional response of rocks is sensitive to the fluid content with very different effective frictional properties in dry and wet conditions. For example, in wet conditions, the frictional response of granite exhibits firm velocity weakening properties between 150 and 350 degrees Celsius, possibly explaining the depth of the seismogenic zone. These are these observations that we would like to capture in a physical model of fault friction in non-isothermal conditions to understand the effect of the temperature activation and the fluid content. We start the model with a description of the real area of contact that supports the shear and normal loads on the fault interface. At first order, the real area of contact, scaled by the nominal area of contact, is a linear function of normal stress, scaled by the indentation hardness of this interface. However, this is modulated by the curvature of the microasperities that support the load. The friction law can be cast as a flow law for frictional sliding that is thermally activated, where the velocity is a very strong function of stress relative to a yield strength that is proportional to the area of contact. The thermal activation can be described as an Arrhenius relationship with an activation energy Q. If we combine the flow law and the expression for the real area of contact, we obtain a constitutive relationship for fault friction in multiplicative form with a power law of stress, power law of the curvature of microasperities, and thermal activation. Another step to allow time dependence is to consider the thermal activation of healing. Healing is represented by the flattening of microasperities, and that can be captured by a thermally activated evolution law with a healing and a weakening term. The healing term is thermally activated with an activation enthalpy H, and contact rejuvenation, which creates weakening, is depends on the velocity of sliding, depends on the width of the gouge layer, and a characteristic strain, here parameterized with the letter lambda. It is useful to look at the steady state frictional response to highlight some important parameters. The steady state response is a function of velocity and temperature to a power exponent, y minus m over p for the velocity that controls the velocity dependence. This parameter is positive. The steady state response is velocity strengthening. If this parameter is negative, the steady state response is velocity weakening. Similar aspect can be found for temperature, which is controlled by the difference between the activation energy for weakening and the activation enthalpy for healing. And when this power exponent Q minus mH over P is positive, it gives rise to temperature weakening. When this parameter is negative, it gives rise to temperature strengthening. So we can look at this multiplicative form of rate and state friction from a different angle. Instead of looking at the velocity as a function of stress, we can look at the stress as a function of all the other dynamic variables. When we do this, we find that the stress is at first order, proportional to normal stress, perhaps with a cohesion term, but modulated by the velocity, the curvature of the microasperities, and temperature. However, these terms are all raised to an exponent of 1 over n. N is very large, and any number that is raised to a small power converges to 1. So essentially, the constitutive law captures the familiar Coulomb friction law simply with the yield strength modulated by 3 dynamic variables. We can also inspect the kinematic friction predicted by this constitutive framework. So let's consider first the evolution law for the radius of microasperities. So this describes the evolution of the radius of curvature of the microasperities. Instead, we can look at the age of contact, which is simply the current radius of curvature divided by a reference rate of growth. And when we do this, the evolution law simplifies to the aging law in closed form. And that provides an estimate for the characteristic weakening distance, which scales with the width of the fold gouge, and also the characteristic strain for contact rejuvenation. We can also expand the multiplicative form through a Taylor series expansion using the Taylor series expansion for the exponential, which is 1 plus x, when x is small. And that provides the additive form of rate and state friction, which is an approximation to the multiplicative form. And that also provides estimates for the familiar velocity dependence parameter and state parameter A and B. So A is mu naught over n, so it's almost the reciprocal of the power exponent for stress. And B scales with A, modulated by power exponents for the curvature of asperities and the rate of healing. So the next step is to expand the model to capture the hydrothermal activation of friction. So for this model assumes that healing happens when the microasperities flatten, and that can happen by many different microphysical mechanisms. So to capture the depth dependence of the velocity dependence of friction, we consider multiple healing mechanisms instead of just one, each of which associated with a certain activation energy and a certain power exponent for the sensitivity to the radius of curvature. In addition, we also consider that contact rejuvenation is thermally activated with a reference strain for the breaking of asperity that is depending on temperature and water content. So For an evolution law like this, there is no closed form solution that allows us to tell the steady state velocity dependence in closed form. However, that can be investigated numerically. And in investigating this problem reveals that the dominant healing mechanism that controls the temperature and velocity dependence of friction is the one that produces the largest radius of curvature of microasperities. So this is exemplified in this figure here, showing 3 different healing mechanisms, each with different colors, as a function of temperature and the asperity size at steady state. And so manipulating the activation energy of each of these mechanisms allows us to control at which depth the transition from velocity weakening to strengthening happens. Furthermore, if we modulate these activation energies as a function of the fluid content, we can also control some changes in the frictional response. So as an example, I'm going to consider the effective frictional properties of granite, which is well understood and described in a series of experiments by Blampede and others that describe the static friction coefficient, the characteristic weakening distance, the velocity direct effect parameter A, and the steady state velocity dependence parameter A minus B as a function of temperature, but also in dry and wet conditions. So we'll start with the dependence, the hydrothermal dependence of the parameter A, which is perhaps the simplest to understand. Simple estimates of this parameter for a single healing mechanism provides A is mu naught over N. So as A is increasing as a function of temperature, well, the corresponding power exponent N must be decreasing. So we capture this effect by a hydrothermal dependence of the power exponent N as follows. Basically, it's proportional to T naught over T, where T is the absolute temperature in Kelvin. And the coefficient of proportionality N naught is a function of fluid content. So fitting these curves provide a dry power exponent of 150 and a wet exponent of 40. And the fluid content is simply interpolated. The fluid content allows us to interpolate between these two values. Next, we consider the steady state velocity dependence of friction as a function of temperature and fluid content. Again, for a single healing mechanism, the steady state frictional parameters A minus B are simply a function of the evolution law parameters P and M and the power exponent N. So in reality, when you have several healing mechanisms, we cannot simply use that equation, but it guides our investigation. And we find the effective steady state dependence numerically. So to capture the transition as a function of temperature from velocity strengthening to velocity weakening to velocity strengthening again, we need to invoke 3 different healing mechanisms, each with increasing activation energies, H1, 2, 3, of values 20, 50, and 550 kilojoule per mole, each associated with different power exponent for the healing term of P1 over M equals 1.5, P2 over M equals 0.85, which is smaller than 1, and P3 over M is 7. Further, the dependence of water content is mostly captured by the dependence of the power exponent N on the partial fluid pressure. The frictional response is very sensitive to the water content and generally described by this, the difference between the activation energy for healing and weakening, in particular Q minus MH over P. when this parameter is positive, it induces temperature weakening. So to capture a temperature strengthening in dry condition and temperature weakening in wet conditions at high temperature, we need to make the activation energy for weakening, Q, a function of temperature. And in fact, it has to increase with temperature. So this is captured by this relationship where the activation energy increases linearly with the absolute temperature in Kelvin. To capture the dependence of fluid content, the activation energy at room temperature has to evolve between about 10 to 20 kilojoule per mole. So this captures the velocity, the temperature dependence of steady state friction, and the main contribution of added fluid content in the fault interface is to create a significant temperature weakening effect at high temperatures. Finally, the model also can predict the characteristic weakening distance for a single mechanism of healing. This is predicted by this simple equation. The weakening distance scales with the thickness of the gouge layer and with the characteristic strain. To capture the temperature and fluid content dependence, this characteristic strain for contact rejuvenation, 1 over lambda, has to be thermally activated as well. So it is given an activation energy, and this activation energy depends on the fluid content. So with this, we can capture the drastic change of orders of magnitude of the characteristic weakening distance from dry to wet conditions. So in wet conditions, the characteristic weakening distance increases by perhaps 2 orders of magnitude at high temperatures. So to conclude, a constitutive law for fault friction derived from thermodynamic principles can capture the hydrothermal activation of healing and weakening. Compared to the dry case, wet granite friction has a much more pronounced steady state velocity dependence, and a marked temperature weakening appears at high temperatures, which is above 350 degrees Celsius. Dynamic changes in temperature and pore pressure, for example, during hydraulic fracturing, can induce changes in frictional behavior, for example, fault stability, that go way beyond the Terzaghi effective stress, sigma minus p, by directly affecting the frictional properties themselves. The evolution of frictional properties at higher temperatures, producing strong weakening during post-seismic slip, remain to be included in this model, and this is direction for future work.